Hello everyone. Uh, I'm going to lecture on relative equilibrium of liquids for linear motion. And for linear motion, there are three cases. We have horizontal motion, vertical motion, and inclined motion. So here we go. First, we have relative equilibrium of liquids. So the explanation here is the containing vessel is moving relative to the ground, but the fluid particles are in equilibrium relative to the surrounding, or are in equilibrium with respect to the surrounding particles. So just like in a bus, the bus may be accelerating horizontally, but the passengers on the respective seats are in equilibrium relative to the other passengers, even relative to the driver of the bus. So I hope that you now have an idea about this topic here. So I'll consider first linear motion. So let's consider horizontally accelerated tank or vessel containing a liquid. So this is the tank and the liquid is at a depth which is assumed to be greater than half the height of the tank. So when accelerated horizontally, rightward or leftward, so it doesn't matter, AX is always positive even if it is accelerated leftward, because if it is leftward, you may position at the back so that it appears to be accelerated rightward. So AX is always positive for this case unless it is decelerated. That becomes a negative value. So when accelerated, just like as a passenger, when the car or bus that you are riding with or riding on accelerates, then you will lean backward. So as a result, you will exert pressure at the back seat. So that's why the pressure increases opposite to the direction of acceleration. So this surface here, initially horizontal. By the way, this remains horizontal surface when the vessel is moving with constant speed or zero acceleration or at rest. But if it is accelerated, then it will assume the surface here, which we're going to investigate the slope or angle that it makes with the horizontal. So if no liquid is spilled, the center here, point of symmetry, remains the same. So we have an angle theta, and we have a particle to be analyzed here. So since this is a particle of small size, but it has considerable weight, so the forces acting on that particle would be its weight. And since it is accelerated to the right, there is a reverse effective force from mechanics and physics opposite to this acceleration, which is mass times acceleration, and mass is weight over g times ax. And because this particle remains at rest, just like a passenger that remains at rest even if the vessel is accelerated, then there must be a force that makes this particle at rest. So that's the, if you are the passenger, then that's the force exerted by your back against the back seat, or the force exerted by the back seat against your back. So in this case, because there are so many infinite number of particles, below this particle here will be so many particles which wait for the transmission of the force exerted the by this particle, pressure force of this particle to the other surrounding particles, so below it. So that is denoted by N, the normal force which makes this particle at rest. So it is perpendicular to this resulting surface. Therefore, if we draw the force triangle, and this is also theta, the angle between the vertical and this normal force. So we have the weight, then the reverse effective force, W over G AX, then the normal force. So this is a right triangle because this is vertical and horizontal, and this is angle theta. So from the figure, tangent theta equals W over G AX divided by W. So cancelling out W, the weight, then the angle assumed by the surface is given by tangent theta equals AX over G. So that's the expression for that angle. So if you're asked to compute for the pressure at this point and the tank is open, so definitely all points on this resulting surface will have zero pressure exposed to the atmosphere. So therefore the pressure at this point here would be gamma, specific weight of liquid, times the depth of that point from the surface of zero pressure. So if we draw a surface or line parallel to the zero surface, or surface with zero pressure exposed to the atmosphere, or even if this surface has pressure, then this surface here, which is parallel to that, will have all its points on the surface will have the same pressure because the vertical distance at all points on the surface to the points on this resulting surface will be the same. So that's why we call that line or surface of equal pressure. So this is the point of symmetry. As long as no liquid is spilled, that remains there, no matter the surface, whatever surface it forms, as long as no liquid is spilled. So when no liquid is spilled, the liquid surface formed always crosses the point of symmetry. Only for this case, of course, it is not closed. So the maximum acceleration, horizontal acceleration corresponding to no spillage would be such that then when the surface crosses the top rear edge, and as long as no liquid is spilled for that case, so you can find the maximum acceleration when the surface crosses the top rear edge of the tank. Then let's proceed to vertical motion. So for vertical motion, so this is the tank. Initially, it contains liquid and it is accelerated upward for this case. So as a result, this time we analyze a prism of liquid, and let's put the forces acting on this prism of liquid when the tank containing the liquid is accelerated upward. So of course we have the weight, and let's call the depth or height of the prism as h. This is a prism of same liquid. I just put boundaries to isolate it so that you can see. The cross-sectional area at the bottom is dA, constant, and the forces are the weight. Because it is accelerated upward, we have the reverse effective force, which is mass times AY, which is downward, also opposite to AY. So W over G times AY. And we have two forces already, which is downward, but this prism of liquid remains at rest. So the third force that makes this prism at rest would be the resulting pressure at the bottom. Pressure force at the bottom, which is pressure at the bottom times the area, which is dA. So since the prism is in equilibrium, summation forces y equals 0. So that is PdA equals W plus W over GAY. So factoring out W, we have weight times quantity 1 plus AY over G. And since weight is equal to specific weight of the liquid times the volume of this prism, where the volume of the prism is area dA times height h. So gamma, specific weight of liquid times dAh. Substitute there. So PdA equals gamma HdA 1 plus AY over G. Then we cancel dA. So therefore, the pressure, the resulting pressure is equal to gamma H times quantity 1 plus AY over G. So we notice that the pressure, gamma H, is the static pressure at a point when the top surface is exposed to the atmosphere. So it is still gamma H. This was the pressure in a static case where there is no acceleration. So this pressure is magnified or reduced by this quantity here, 1 plus AY over G. So when the vessel is accelerated upward, then the pressure at any point is same pressure, static pressure, times quantity 1 plus AY over G. So plus if the acceleration is upward, minus if acceleration is downward. So pressure therefore is gamma H1 plus AY over G if it is accelerated upward. The pressure at any point for vertically accelerated vessels, and gamma H times 1 minus AY over G if it is accelerated downward. So for this tank, if we want to compute for the pressure at B and the tank is accelerated upward, then the pressure at B is, in general, gamma times big H, the depth, times quantity 1 plus AY over G if it is accelerated upward. Then gamma times big H, quantity 1 minus AY over G is if it is accelerated downward. So pressure at B is also, gamma big H is pressure at B, static pressure at B, times quantity 1 plus AY over G if it is accelerated upward. Static pressure at B, quantity 1 minus AY over G if it is accelerated downward. So where PBS is the static pressure at B. So in general, the pressure at B is static pressure at B, quantity 1 plus minus AY over G. So remember that use plus when the vessel is accelerated vertically upward, minus if accelerated downward. And finally, for inclined motion case, so we have an inclined plane and the angle of inclination of the plane is beta. And we have a vessel here. It contains initially with this liquid. This is horizontal surface. When the vessel is either at rest or in motion with constant speed along the inclined plane. So assuming it accelerates up the hill. So again, there are two components of acceleration, horizontal and vertical. But remember, if it is accelerated down the hill, only the y component can be treated negative, but the horizontal component is always positive. Because if it is accelerated down the hill and it is going to the left, it's like going to the right if you position yourselves at the back. So that's why up the hill or down the hill, AX is always positive. So horizontal surface when not moving or moving with a constant speed, then if it is accelerated along the inclined plane up, then the surface will assume again an angle with the horizontal in this form opposite to AX. So take note that AY has the y component of acceleration has nothing to do with the resulting surface. Only the pressure is either increased or reduced depending on the component of AY in the explanation here for vertical motion. So only AX affects the surface, the slope of the resulting surface. AY only affects the resulting pressure at any point on the vessel. So the angle is assumed to be theta, so we analyze another particle on the surface. This particle is again at rest, so it consists of its own weight. Then since there is y component of acceleration which is upward, so we have reverse effective force which is downward. Since there is ax rightward, so reverse effective force which is leftward, mass times acceleration. So going down, w over g ay, then going to the left, w over g ax. And since the particle remains at rest, the resultant here is down to the left. So there should be a normal force that is exerted by this particle on the with respect to the bottom particles. So it is perpendicular to the resulting surface. And if we draw the force triangle again, we have weight W over G AY and W over G AX to the left, then the normal force. Then the angle between the vertical and the normal force is theta. And since this is a right triangle, tangent theta equals W over G AX divided by quantity divided by W, quantity W, plus W over G AY. So simplifying, we have W over G AX over W quantity 1 plus AY over G. Then we can cancel W. So we have AX over G plus minus, or G plus AY over G. Canceling out G, so tangent theta equals AX over G plus AY. In general, tangent theta is AX over G plus minus AY. Use plus in the denominator if the y component of acceleration is upward, then use minus if the y component of acceleration is downward. AX is always positive. So where AX is A cosine beta and AY is A sine of beta. So that's it for this situation. Then let's have cases of drawing the resulting liquid surfaces. So for this case, so take note that the vessel is open to the atmosphere and the depth of liquid is greater than half the total depth of the tank. We will call the depth as capital D and the empty depth as K, and the overall height of the tank as big H. So the length of the tank is L. This is rectangular and perpendicular to the board, it may be B. So if it is accelerated horizontally, the surface remains horizontal or flat when AX is 0 or the speed is constant, uniform speed. By experience, if you are riding on a car or bus that is moving with constant speed and you have a cup of soft drinks, the cup of soft drinks will have horizontal surface when the car is moving with constant speed. So for this second situation, this is the situation when AX over G is less than 2K over L. So this is the point of symmetry. No liquid is spilled for this situation. So call that Y, where Y is less than K. So this is the situation where when AX over G is less than 2K over L. Why less than 2K over L? Because when the surface crosses the top rear edge here, then tangent of theta would be K over L over 2. K over L over 2 is 2K over L. So for this case where it crosses below the top rear edge Y, so that's why tangent theta is AX over G, and AX over G should be less than 2K over L. When it exactly crosses the top rear edge and this point of symmetry here, because no liquid is still spilled, then that's the situation when AX over G is exactly equal to 2K over L, or exactly equal to K over L over 2. So the corresponding value of AX is the maximum acceleration without spilling any liquid for this open tank. Then when the situation is such that AX is greater than the value of AX here without spilling any liquid, but the surface still crosses above this front bottom corner, then that's the situation when AX over G is less than big H over L. That's it. But when, and certain volume of liquid is spilled for this case already. Then when the surface exactly crosses this bottom right corner, that's the situation when AX over G is exactly equal to H, capital H over L. Then when the acceleration is still increased such that it now crosses the bottom of the tank somewhere here, and so great volume of liquid is spilled for this case, this is the situation when AX over G is greater than H over L already. So that's it for this open tank, and these are the different cases. Now how about for this tank with a small opening here? It contains with liquid again with depth greater than half of the total height. So the length is still L, the depth is capital D, and this is K. So this is also big H. So we have the point of symmetry. So again, when the surface is horizontal, AX 0 or constant speed, then this is the situation when AX over G is less than 2K over L, just like above. Then when it exactly crosses this corner here, that's the situation when AX over G is exactly equal to 2K over L. When the acceleration is increased further, then this is now the resulting surface because no liquid is spilled. So this is now the resulting surface. This is the, and let's call this distance X, and that is the imaginary liquid surface extended. So let's call that X. So this is the situation when 2K over L is less than AX over G, and AX over G is less than big H over X, because the angle is definitely, tangent theta is this value here, which is less than H over X. Then when it exactly crosses this corner, that's the situation, this is still called X. That's the situation when AX over G is exactly equal to big H over X. And when the acceleration is further increased, that it crosses the top and the bottom like this, and that's the situation when AX over G is greater than big H over X, where X is still the distance of the point where the surface crosses the top cover from this right point. So that's for this situation here. So note that for this vessel here with an opening, the initial volume of air in the tank is always equal to the final volume of air in the tank because no liquid is spilled. Or in other words, the initial volume of liquid in the tank is equal to the final volume of liquid in the tank. So that's the same thing. So of course, all points on this liquid in this air space is 0 because there is an opening and the opening is exposed to the atmosphere. And we have here a situation, we have a full tank, closed tank without partial pressure. So imagine the driver is here. So the front face of the driver will be same, 0 pressure. But as soon as the tank, full tank is accelerated to the right, then the driver will lean backwards so that the pressure at all points will be exerted to the left so that the pressure increases. So the surface, imaginary surface starts with here because the pressure here is initially 0 and it increases there. So that's an imaginary surface. the pressure at all points here will increase gamma times this vertical distance. So tangent of theta, this theta is still AX over L if the length is L, or AX over G rather. And it is also equal to, tangent theta is also equal to this vertical distance over L if this is L. Then full and with partial pressure. So the partial pressure is first converted into pressure head, PO over gamma, because so that we can locate zero pressure, which is here. So this is the surface of zero pressure, and this is equal to initial pressure, partial pressure over gamma of this liquid here. And this is the resulting imaginary liquid surface again, and this is PO over gamma. So tangent theta equals AX over G, same principle. So that's the way how to solve for theta. So if you want to compute the pressure here, maximum pressure here, it is equal to gamma times this vertical distance plus gamma times quantity, this vertical distance, plus PO over gamma plus this height, which is denoted maybe big H. So that's the maximum pressure here. Then for this tank with a small opening here, full, so the surface always crosses points of equal pressure, which is zero. So initially the imaginary surface would be horizontal through this point because pressure is zero on this level. Then when it is accelerated to the right, then it will assume an angle through this point because this has zero pressure. So this is the resulting imaginary surface. And the slope tangent theta is still AX over G. So that you can compute for this vertical distance or this vertical distance here. Then finally, if you have a U-tube with identical vertical legs, partially filled, when accelerated to the right, then this will lower and this rises by the same amount because the legs are identical, same diameter or same size. So tangent theta is still AX over G. So the legs are identical for that case. Then finally, if you want to compute the pressure at B, then all you have to do is, because the pressure here will always zero exposed to the atmosphere, all you have to do is compute this vertical distance, and we'll call that HB. And the pressure at B is gamma of the liquid times HB. So that's it for this lecture, and after this we'll have examples.